Hello everyone and welcome back. Today we are going to be talking about one of my favorite subjects, which is orbits. Yes! Specifically, we're going to be talking about Keplerian orbits today. So an orbit is just the trajectory of an object due to the influence of gravity. Since we're talking about Keplerian orbits, we're talking about Newtonian gravity. So Kepler's laws were empirical observations that were made by Kepler, and then these were later kind of mathematically described by Newton's law of gravity. Now you can use Einstein's theory of general relativity, which is a more detailed theory about gravity, to describe orbits, but that's not usually necessary. There are situations in which it will make a difference. Very famously in the solar system, this does affect Mercury's orbit. If you've ever heard of the planet Vulcan, and no, I don't mean this type, I mean in our solar system. So basically, based on some anomalies that we saw in Mercury's orbit, we thought that there was going to be a planet interior to Mercury, and this hypothetical planet was named Vulcan. However, it later turned out that these anomalies in Mercury's orbit were actually due to general relativity and the departure basically from Newtonian gravity. But in general, we don't need to worry about this, and so we're just going to be talking about Newtonian gravity and Keplerian orbits today. Well, orbits, at least closed orbits, make this wonderful shape called an ellipse. And this is described by Kepler's first law, and so basically an ellipse has two focus points. And the star, or the body that the planet is orbiting, is going to be at one of those focuses. Now, if you just think about a particle and you want to describe it, kind of what it's doing, you're probably most familiar with Cartesian coordinates. So this is x, y, and z, right? These are rectangular coordinates. You just give an x value, a y value, and a z value, and that will specifically define the location of an object relative to the reference axes. If you also want to give that object's trajectory, you need to know not only its position in x, y, and z, but also its velocity in each of those directions as well. And so that's basically 6 parameters, independent parameters, that you need to know to specifically define the object. And that is because there are 6 degrees of freedom that we call it. So you can think of it just the 3 position and the 3 velocity things that you need to know. So equally then, if we want to describe that same object uniquely using an orbit, we need to have 6 independent parameters to define that orbit. For the same reason, because we need to cover all 6 of those kind of degrees of freedom, or different ways that it could be located and moving. So these parameters that we choose are called the Keplerian orbital elements. Now, in order to define an orbit, you need to define a reference body. Now, typically for a planet and a star, we'll just take the star to be the reference body, but of course you don't have to. So the first Keplerian orbital element is the Semimajor Axis, or A. So an ellipse is described by 2 axes, the major axis, which is the longer one, and the minor axis, which is the shorter one. And semi means half. So this is basically just half of the long axis of the ellipse. If you were to think about the special case of an ellipse that is circular, then the semi-major axis would just be the radius, and it would also be equal to the semi-minor axis. So basically you can just think of the semi-major axis as the longer radius of the ellipse, if you like. This is also typically described as the kind of average distance of the planet from the star. Next, we have the eccentricity, which is described by E. So E is just a unitless value. So the semi-major axis was a distance. E is a unitless value that describes the non-circularity of the ellipse. So that basically means that E equals 0 is a perfectly circular ellipse, but as E goes towards 1, it becomes more and more non-circular. And you can only have a closed orbit if E is less than 1. If E equals 1, then you have a parabolic orbit, and if E is greater than 1, you have a hyperbolic orbit, and those are both unbound orbits. You can also think of E as describing the difference between what we call the apoapsis and the periapsis. So apoapsis is when it's furthest away, and periapsis is when it's closest. And so a more elliptical orbit, those will have a larger difference. Fun fact, you may have heard terms like perihelion, perigee, periselene, things like that. So basically, those are all very specific relative to a specific body. So perihelion is relative to the sun, perigee is relative to the earth, periselene is relative to the moon. So you can use that, but also the general term is periapsis. So periapsis is for any orbit. Next, we have inclination, or I. An inclination is described as an angle, and so it can be degrees or radians. And so basically it describes the tilt of the orbital plane relative to some reference plane. So the orbital plane is basically what we mean if you drew a line between the planet and the star at all points in time that would lie within the orbital plane. So it would just be the planet going around the star. Now, if you want to tilt that plane relative to some reference plane, then you introduce some inclination. Now, your reference plane can be anything that you want it to be. It's an arbitrary reference. So if you only had, for example, one planet orbiting a star, you might pick the reference plane to be the orbital plane, in which case your inclination is 0 and it doesn't really matter. But there are other ways you might want to choose the reference plane. For example, you might want to choose the stellar equator because stars aren't perfectly spherical and they do tend to have a bulge, and that can introduce some higher order effects that we're not going to get into, but you might want to choose that. If there's multiple planets, then they are not all going to have the same orbital plane, and so you might want to choose some sort of average plane. If you're observing a system, we typically use the reference plane as the sky plane, which is just what it sounds like, assuming that the sky is the reference plane. And so, for example, for planets that are transiting, that is, they're passing in front of their star and we're seeing an edge on orbit, the inclinations are usually close to 90 degrees because we are taking the sky plane to be the reference plane. Next, we have the longitude of the ascending node, which is described by capital omega. And this is also an angle. And this basically gives the orientation of the orbital plane. So the inclination gives the tilt, and then you could rotate that plane in any direction, right? So we need some sort of direction to give it in order to define it. And so we use this, the longitude of the ascending node. So the ascending node is just where the orbit passes upward through the reference plane. There's nothing special about ascending node. You can pick the descending node as well. It's going to just be on the other side, but you just need to pick something, and so we have decided on using the longitude of the ascending node. And this is measured relative to some reference direction. So just like the reference plane, the reference direction is arbitrary, and you can choose it to be basically whatever you want. For example, in the sky plane, you might choose the reference direction to be in the direction of some given star. That's not the star you're observing, but you can pick anything. And then you're going to measure this angle relative to that reference direction. Now, if you'll think, we said that you could take the reference plane to be the orbital plane, in which case you have an inclination of 0, in which case the node where the orbit passes through the reference plane doesn't really exist. So in that case, this longitude is undefined, but it's commonly taken to be 0, just meaning whatever your reference direction is, to kind of make it easier to think about. But yes, in that case, it would be technically undefined. Okay, next we have the argument of periastron, or periapsis, and this is little omega. And this basically gives the orientation of the ellipse within the orbital plane. So if you have a elliptical orbit, it's going to have one place that's longer and one way that's shorter. And then in the orbital plane, how that is oriented can be different, right? And so the argument of periapsis tells us how it is oriented within the orbital plane. It is also an angle, and it's measured between the ascending node and periapsis. So remember, the ascending node is where the orbit passes upward through the reference plane. So you'll take that to be 0, and then you'll measure an angle to the periapsis. However, we said that in some cases you don't actually have a ascending node, right? If the reference plane is your orbital plane. But again, in that case, we would typically take big omega, or the longitude of the node, to be 0, and so you could take the argument of periapsis to also be 0 in that case. Now, I said an ellipse has a kind of preferential direction because it's longer in one way and shorter than the other. But if you think about an orbit with e equals 0, then it's circular, then it doesn't have any preferred direction, right? Circles are rotationally symmetric. In that case, the argument of periapsis is going to be undefined. Again, similarly as to when the longitude of the ascending node is undefined, you can take the argument of periapsis to be 0. Sometimes it's taken to be 90, but it's technically undefined for a circular orbit. Okay, so the 5 parameters that we've already discussed basically kind of give you the size, shape, position, orientation of the orbit. So that orbit is kind of the trajectory at all possible times of the planet. So then you're going to need something to tell you where the planet actually is. And so we call this the true anomaly. This is another angle, and the true anomaly is just the angle, basically, relative to usually the periapsis of where the body is at a given point in time. Sometimes you'll hear this given point in time called the epoch. They'll call it true anomaly at epoch. It just means at a specific point in time, this is where the planet is, defined by an angle. And if you know that at one single point in time, then you can calculate its location at any other point in time because the orbit is defined, you know how it's going to travel, and then you can calculate it. So that's it. With these 6 parameters, you have defined a unique orbit. Now you may have heard of some other orbital parameters and you're thinking, I thought you said you only need 6, but I can think of all these other orbital parameters. Well, I said you need 6 independent orbital parameters, but there are other orbital parameters that we use, sometimes in different ways than these orbital parameters, but they're related to these orbital parameters, so they're not independent. For example, there's the period of an orbit, so that's how long it takes the planet to complete one revolution of its orbit. This is related to the Semimajor Axis. Thanks, Kepler. There's also something called the longitude of periapsis. So if you'll remember, we talked about the longitude of the ascending node and the argument of periapsis. So now we're talking about the longitude of periapsis. How is that different? Well, it's actually a compound angle, and it's actually just the sum of the longitude of the ascending node and the argument of periapsis, because those angles are measured in different planes. So it's not exactly a single angle, it's a compound angle. It's usually represented by this letter, which people have different names for. It's sometimes called curly pi, it's sometimes called bar pi, it's sometimes called pomega. I like to use pomega myself, but I mentioned that the eccentricity tells you the difference between the periapsis and the apoapsis, and the semimajor axis kind of tells you the scale of that. So basically, the eccentricity and semimajor axis give you the same information as having the apoapsis and periapsis, or in some combination. So for example, a lot of times with solar system objects, you will see the perihelion defined by Q, and that is often used to help characterize the orbit. I mentioned the true anomaly, which is the angle that the body is actually making relative to the periapsis. But there are other ways of measuring the location of the body. So you can use what's called the mean anomaly. So the mean anomaly probably might make the most sense kind of conceptually. It just gives the fraction of the orbit that it's completed. And so it goes from 0 to 2 pi, so it goes around a full revolution evenly in time. So it's evenly spaced in time. The true anomaly is not, because the planet doesn't move with a consistent speed. It moves faster when it's near perihelion or periapsis, and it moves slower when it's at apoapsis. So true anomaly doesn't vary smoothly in time, but mean anomaly does. However, mean anomaly isn't a physical angle. There's no angle you're actually measuring. It's just a representation of how far along in its orbit the planet is. There's also something called the eccentric anomaly, which is a little confusing, but basically you can take what's called a reference circle. So it's basically the circle that would perfectly kind of encapsulate the ellipse. And then you can measure the angle of the body's location projected onto the reference circle from the center of that circle, and that's called the eccentric anomaly. The eccentric anomaly is related to the mean anomaly via something called Kepler's equation, which is here, and this equation cannot be solved analytically, it has to be solved numerically. Also, all of those that I mentioned, the true anomaly, the mean anomaly, and the eccentric anomaly are all measured relative to periapsis. If you wanted to measure them relative to the reference direction instead, you totally could, but then they would be called longitudes instead of anomalies. Okay, so that might have been a little confusing, but really, that's it. If you have a planet and a star, that's it. It's like clockwork, literally. You have these parameters that defines the orbit, and they will forever be on that exact orbit. You can look at any point in time into the future and know exactly where that planet is going to be. However, real life is rarely that simple, of course. So anything that can affect this orbit will change it from these orbital parameters, and we call that non-Keplerian kind of perturbation. So non-Keplerian changes to the orbits. Because these Keplerian parameters assume a static, unchanging, perfect orbit. So some things that might do this, for example, I mentioned earlier that stars are not perfectly spherical, and so the change in gravity due to their shape can have effects on the orbits. Other planets in the system, like I said, I talked about Vulcan and Mercury earlier, so we thought that there was a planet causing that change. Turned out not to be, but we did use that to discover Neptune. And we use it in exoplanet systems all the time, how the planets interact with each other and change their orbits. It could be passing stars or influences from the galaxy. So really, there are lots of things that can change these orbits, and it's really fun and exciting to study, because if you don't know, this is what I personally study. I am a dynamicist, and so I am interested in the orbits of planets. But the very basics are what we covered here, and so I hope you learned a little bit of something about orbits, and I hope you will come again next time, and I'll see you soon. Bye!